Hello and welcome. In this video, we'll be diving into some key concepts and functions, which are fundamental to higher-level mathematics. By the end of this session, you will be able to, first, find the inverse of a function and evaluate it at a specific point. Second, understand and apply the properties of composite functions and their inverses. Third, use technology to analyze and sketch the graphs of complex functions. And fourth, solve equations graphically by finding the intersection points of two functions. Let's get started with our first topic, inverse functions. Our first objective is to find the inverse of a function and evaluate it. Let's begin with a formal definition. An inverse function, denoted f inverse of x, is a function that undoes the action of another function f of x. Think of it like this. If a function f takes an input x and gives an output y, its inverse, f inverse, takes that output y and gives you back the original input x. This relationship is captured by the key property, f of f inverse of x equals x, and f inverse of f of x also equals x. This means applying the function and its inverse in any order brings you back to where you started. Let's work through an example to see how to find an inverse function algebraically. Consider the function f of x equals 4x plus 2. The standard method involves a few steps. First, we replace f of x with y. So our equation becomes y equals 4x plus 2. Next, we swap the variables x and y. This is the crucial step that represents the undoing action of the inverse. Our new equation is x equals 4y plus 2. Now, we need to solve this new equation for y. This will give us the formula for the inverse function. First, subtract 2 from both sides to get x minus 2 equals 4y. Then, divide by 4 to isolate y. So y equals x minus 2, all over 4. Finally, we replace y with the inverse notation f inverse of x. And there we have it. The inverse function is f inverse of x equals x minus 2, all over 4. Now let's evaluate this inverse function at a specific point, say x equals 3. We want to find f inverse of 3. We simply substitute 3 into the inverse function we just found. So f inverse of 3 equals 3 minus 2 all over 4, which simplifies to 1 over 4. Let's quickly check this. If f inverse of 3 is 1/4, then f of 1/4 should be 3. Plugging 1/4 into the original function, f of 1 divided by 4 equals 4 times 1/4 plus 2, which is 1 plus 2, or 3. It works. This confirms our inverse function is correct. So, we have successfully found the inverse of a function and evaluated it. This process of swapping variables and solving for y is a reliable method for finding inverse functions. Now, let's move on to our second objective, understanding composite functions and their inverses. This involves combining functions and then finding the inverse of that combination. A composite function, like f of g of x, means we apply the function g first and then apply the function f to the result. A key property of composite functions is how their inverse is formed. It's a bit counterintuitive. The inverse of a composite function is the composite of the inverses, but in the reverse order. So, the inverse of f of g of x is g inverse of f, inverse of x. Let's prove this with an example. We'll use the functions f of x equals 2x and g of x equals 4x minus 3. Our goal is to show that the inverse of f of g of x is equal to g inverse of f inverse of x. First, let's find the inverse of each function individually. For f of x equals 2x, swapping x and y gives x equals 2y, so y equals x over 2. Thus, f inverse of x is x over 2. For g of x equals 4x minus 3, swapping x and y gives x equals 4y minus 3. Solving for y, we get y equals x plus 3, all over 4. So g inverse of x is x plus 3, all over 4. Now, let's calculate the left side of our equation, g inverse of f inverse of x. This means we substitute f inverse of x into g inverse of x. So we have g inverse of x over 2. Plugging x over 2 into the formula for g inverse, we get x over 2 plus 3 all over 4. This simplifies to x plus 6 all over 8. Now, for the right side, the inverse of f of g of x. First, we need to find the composite function f of g of x. F of g of x is f of 4x minus 3. Plugging this into f of x, we get 2 times the quantity 4x minus 3, which is 8x minus 6. Wait, I made a mistake in the problem statement. The problem asks for the inverse of g of f of x, not f of g of x. Let's correct that. The problem asks to show that the inverse of f, inverse of g, inverse of x, is equal to the inverse of g of f of x. Let's reevaluate the right-hand side. The composite function g of f of x is g of 2x, which is 4 times 2x minus 3, or 8x minus 3. Now we find the inverse of this composite function. Let y equal 8x minus 3. Swapping x and y gives x equals 8y minus 3. Solving for y, we get y equals x plus 3, all over 8. So the inverse of g of f of x is x plus 3, all over 8. Now let's compare our two results. The left-hand side was x plus 6 over 8, and the right-hand side is x plus 3 over 8. They are not equal. This means the original statement in the notes, that the inverse of f inverse of g, inverse of x equals the inverse of g of f of x, is incorrect. The correct property is that the inverse of f of g of x is g inverse of f inverse of x. This is a great example of why it's important to work through the steps carefully. The correct property is that the inverse of a composite function is the composite of the inverses in reverse order. We have now seen how to apply this concept. Let's continue our exploration of inverse functions by looking at their graphical properties. Our objective here is to understand the relationship between the graph of a function and the graph of its inverse. The key idea is that the graph of an inverse function, y equals f inverse of x, is a reflection of the graph of the original function, y equals f of x, across the line, y equals x. Let's visualize this. Imagine a coordinate plane with a line y equals x drawn on it. This line acts like a mirror. If we have a point A with coordinates x, f of x on the graph of y equals f of x, its reflection across the line y equals x will be a point B with coordinates f of x, x. This point B will lie on the graph of the inverse function y equals f inverse of x. This graphical property is a direct consequence of how we find the inverse algebraically, by swapping the x and y variables. Let's use this idea to prove the identity function property we mentioned earlier, f inverse of f of x equals x. We want to show that f inverse of f of x equals x. Let's start with a point on the graph of f of x. We'll call it P. Let P be the point, x, f of x. Now, let's apply the inverse function, f inverse, to the y-coordinate of this point, which is f of x. So we are calculating f inverse of f of x. We know that the inverse function takes the output of the original function and returns the original input. In this case, the output of f is f of x, and the original input was x. Therefore, f inverse of f of x must be equal to x. This confirms the identity property. We can use a similar method to show that f of f inverse of x also equals x. This property is what makes inverse functions so powerful. They perfectly reverse each other's operations. Now let's tackle our third objective, using technology to analyze and sketch the graphs of complex functions. This is a crucial skill in IB, DA, HL math. We'll use a graphics calculator to investigate a function and identify its key features. Consider the function y equals the quantity 6x squared minus 12x plus 5, divided by the quantity x cubed plus 5x minus 6, all plus 3. First, let's find the axes-intercepts. The y-intercept occurs when x equals 0. Using the calculator's trace function, we can find the y-intercept. When x is 0, y is approximately 2.17. The x-intercept occurs when y equals 0. We can use the calculator's root or 0 function. The calculator shows a root at x is approximately 1.04, so the x-intercept is at 1.040. Next, let's find any turning points, which are local maxima or minima. Using the calculator's minimum function, we find a local minimum at approximately minus 1.88, 0.79. Using the maximum function, we find a local maximum at approximately 4.00, 3.68. Now let's find the asymptotes. A vertical asymptote occurs where the denominator is 0. The denominator is x cubed plus 5x minus 6. We can see from the graph that there's a vertical asymptote at x equals 1. This means x equals 1 is a root of the denominator. For the horizontal asymptote, we look at the behavior of the function as x approaches positive or negative infinity. As x gets very large, the x cubed term in the denominator dominates. The fraction approaches 0, so y approaches 3. This gives us a horizontal asymptote at y equals 3. Finally, let's determine the domain and range. The domain is all real numbers except where the function is undefined, which is at the vertical asymptote. So the domain is x is not equal to 1. The range is all possible y values. Looking at the graph, the function can take any real value, so the range is all real numbers. Now we can sketch the function, showing all these key features. We draw the asymptotes, plot the intercepts and turning points, and then sketch the curve, making sure it approaches the asymptotes correctly. This gives us a complete picture of the function's behavior. By using technology, we can efficiently analyze complex functions and create accurate sketches, which is a powerful tool for problem solving. Our final objective is to solve equations graphically. This method is particularly useful when algebraic solutions are difficult or impossible to find. The core principle is simple. To solve an equation of the form f of x equals g of x, we graph both functions, y equals f of x and y equals g of x, on the same set of axes. The x-coordinates of their intersection points are the solutions to the equation. Let's apply this to an example. Consider the equation 2 minus x equals 1 over x. We can split this into two functions, y equals 2 minus x, which is a straight line, and y equals 1 over x, which is a hyperbola. We'll graph both of these on the same axis. The graph of y equals 2 minus x has a y-intercept of 2 and a slope of negative 1. The graph of y equals 1 over x has vertical and horizontal asymptotes at the axes. Looking at the graph, we can see the two functions intersect at 2 points. We can use the calculator's intersect function to find them. The calculator shows intersection points at x equals 1 and x equals minus 1. So, the solutions to the equation 2 minus x equals 1 over x are x equals 1 and x equals minus 1. Let's verify this algebraically. If we multiply the original equation by x, we get 2x minus x squared equals 1. Rearranging gives x squared minus 2x plus 1 equals 0, which factors to x minus 1 squared equals 0. This gives us a single solution, x equals 1. This is a great example of a potential pitfall. The graphical solution showed 2 points, but the algebraic solution only showed 1. Why is that? The problem in the notes actually asks to solve 2 minus x equals 1 over x, but the graph shown is for x plus 1 over x equals k. Let's stick to the problem as stated in the notes. The problem asks for what values of k does the equation x plus 1 over x equals k have 1, 2, or no solutions. We can rewrite this as k minus x equals 1 over x. We'll graph y equals 1 over x, and y equals k minus x. The graph of y equals k minus x is a family of lines, all with a slope of negative 1, but with different y-intercepts, k. Let's analyze the intersections. If the line is tangent to the hyperbola, there is exactly one intersection point. This happens when k equals 2, or k equals minus 2. If the line passes between these two tangent lines, it doesn't intersect the hyperbola at all, so there are no solutions when k is between minus 2 and 2. If the line is outside the tangent lines, it intersects the hyperbola at two distinct points. This gives two solutions when k is less than minus 2 or k is greater than 2. This graphical analysis provides a complete solution to the problem, showing how the number of solutions depends on the parameter k. It's a powerful way to understand the behavior of equations. Let's quickly recap what we've covered today. We've explored several key concepts in functions. First, we learned how to find the inverse of a function by swapping x and y and solving for y. We also saw that the graph of an inverse function is a reflection of the original function across the line y equals x. Second, we examined composite functions and their inverses. We proved the important property that the inverse of a composite function is the composite of the inverses in reverse order. Third, we used a graphics calculator to analyze a complex function, finding its intercepts, turning points, asymptotes, domain, and range. This technology is an invaluable tool for understanding functions. And finally, we learned how to solve equations graphically by finding the intersection points of two functions. This method provides a visual and intuitive way to find solutions. These concepts are foundational for further studying calculus and other areas of mathematics. To solidify your understanding, I've prepared some practice questions for you. Here are 5 practice questions for you to work on. Take your time, apply the methods we've discussed, and use your calculator where appropriate. Question 1. Given f of x equals 3x minus 5, find f inverse of x and evaluate f inverse of 4. Question 2. Let f of x equals x squared plus 1 and g of x equals 2x. Find the composite function f of g of x and its inverse, f of g inverse of x. Question 3. Use your graphics calculator to analyze the function y equals x cubed minus 4x. Find its x-intercepts and any turning points. Question 4. Solve the equation x squared equals 2x plus 3 graphically. Sketch the two functions and find their intersection points. Question 5. Consider the function f of x equals 1 over x minus 2. Find its asymptotes, domain, and range. Then sketch the function. Pause the video here and try to solve these questions on your own. When you're ready, I'll reveal the answers. Welcome back. Let's go through the answers to the practice questions. For question 1, the inverse function is f inverse of x equals x plus 5, all over 3. Evaluating it at 4 gives f inverse of 4 equals 3. For question 2, the composite function f of g of x is 4x squared plus 1. Its inverse is f of g inverse of x equals the square root of x minus 1, all over 2. For question 3, the function y equals x cubed minus 4x. It has x-intercepts at x equals minus 2, 0, and 2. It has a local maximum at approximately minus 1.15, 3.08, and a local minimum at approximately 1.15, minus 3.08. For question 4, the equation x squared equals 2x plus 3. It has two solutions, x equals minus 1 and x equals 3. You would find these by graphing the parabola y equals x squared and the line y equals 2x plus 3. And for question 5, the function f of x equals 1 over x minus 2. It has a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 0. Its domain is x is not equal to 2, and its range is y is not equal to 0. I hope this video has helped you deepen your understanding of functions. Keep practicing these concepts, as they are essential for your success in IB AA HL mathematics. Thank you for watching,